I wanted to pick back up right here for just a second where we left off on the last video. I think that I misspoke, and so I just wanted to clarify this middle bond where you have the sp hybridized orbitals that are overlapping with each other. That is your sigma bond, and that is the first bond that forms and the strongest bond. And then your side-to-side overlap from your pi bond is weaker, but it does make the entire bond stronger. So in a single bond, you only have one sigma bond, and then when you get a double bond, you still have that sigma, which is the strongest, but then you add a pi to it, so you're adding a little bit of strength. And then in this triple bond, as you see here, you have a sigma and two pi bonds, and so that's going to be stronger than a single sigma bond. Alright, in this picture here, all this is showing is resonance. And so remember, resonance is when the double bond can move to a different place, and it is moving. So in this example, the double bond could be in the three places you see it in the first section, or the three places you see it in the second section. What's really happening is that it's constantly moving between those. And if we go back and look, we know that that double bond is really this pi bond, this side overlap. So if you can imagine, you have lots of unhybridized p orbitals in this circle. So each of these carbons that you see has an unhybridized p orbital. And right here, what we're seeing is an overlap between these two. Unhybridized p orbitals here and here, and they're overlapping, and then here and here, and they're overlapping. So when we see a double bond, we're seeing that overlap of the unhybridized p orbitals. But the other p orbitals could just as easily overlap. So let me show that in just a different color. Okay, so the overlap could be over here too, right? Or over here. Or over here, and we know in reality it's happening all the way around at the same time, and so we draw it as you see in this last one, showing that the double bond's neither here nor there. It's moving all the way around in what we call delocalization of these electrons. And so this is just kind of a fancy way to draw the resonance in this one particular structure, which is called benzene. So sorry about that error at the end of the last video. I think I said sigma when I should have been saying pi, or vice versa. Alright, next topic is polarity. So we're going to be looking at when bonds are polar and when they are nonpolar. And so a bond being polar means that the shared electrons, so this is an important distinction here because we're still talking about covalent bonds, but the shared electrons spend more time around the most electronegative element in the chemical bond. And remember on the periodic table that fluorine is that most electronegative element. So if there are elements that are closer to fluorine, those are going to be your more electronegative, and then the ones further from fluorine are going to be less electronegative. This unequal sharing gives the more electronegative element a slightly negative charge. We call it a partial charge, and we use this symbol sigma to show that. So a partial negative on the more electronegative element, and then the less electronegative element will have a partial positive charge. Now these charges are called partial because it's not like one of the elements is completely taking the electrons away, but they're just spending more time around that element, and so that's why it's a partial charge. If it was a complete charge, then we would have ions, and it would be an ionic compound. But we're still talking about covalent compounds, still sharing, just not sharing equally. Here's an example of a polar bond in hydrochloric acid, or HCl. Chlorine is much more electronegative than hydrogen, so chlorine has the electrons around it most of the time. We use these kind of symbols to show what's going on. So this is one way to show, and it's an arrow. the arrow always points toward the most electronegative element, which in this case is chlorine, and then at the tail we have a positive sign, and that just reminds us that that is where the partial positive charge is, because the electrons are going with the arrow. The greater the difference in the electronegativity, the larger the dipoles are going to be. So if this partial negative here is, I'm just making up numbers, but let's say partial negative 0.75. So the electrons spin 75% of the time over there. If you replace this with fluorine, which is more electronegative, then that partial negative would go up to a higher value. It still would never be 1 because it's not like the element is completely taking the electrons and they're spinning 100% of the time over there. And if that did happen, that would be an ionic compound. So it wouldn't be a partial charge any longer. All right, polar and nonpolar molecules. So if we look back, this molecule, HCl, only has a single bond in it. But what we want to talk about here is whether or not the entire molecule is polar. And we're going to talk about molecules with lots of bonds in them, not just single bonds like we saw there. If a molecule is polar, it has what is called a dipole moment, which is represented by the symbol you see there. The dipole moment is equal to the value of the net partial charge at each end of the molecule. Okay, so if we look back, we would talk about the value of this partial charge here and here, and those would be Q. And it's the absolute value of those, and they should be equal, of course. So we're talking about the absolute value of the partial charge is Q, and then R is the distance between the positive and the negative poles of the molecule. So again, if we look back, R would be the distance between this H and the Cl in a very simple example. And we'll look at some more complex molecules. You will not be required to calculate dipole moment. Okay? All you really need to understand about dipole moment is that if a molecule is polar, it has a dipole moment. It has a value for this U. And if it's nonpolar, this value is 0. And the more polar it is, the higher this value will be. So how do you know if a molecule is polar? Two things you've got to know. You've got to know if the bonds are polar inside the molecule. So is there an even sharing or an uneven sharing going on? And then what about the overall molecule? What's the shape? So we'll look at individual bonds. Are they polar or not? And then we'll look at the shape. And those two factors will help us determine if the molecule is polar. For example, HCl. We just looked at this one. So we know that the bond is polar. We know that the chlorine pulls the electrons toward itself, the ones that are shared in the middle, and hydrogen is left electron poor. So this molecule is polar. The bond dipoles do not cancel. So what that means is the pull from chlorine, as it's pulling the electrons to itself, there's nothing to cancel that on the other side. For example, if, and this would never happen, but if there was another chlorine on the other side of that hydrogen that was also pulling the electrons, those pulls might cancel. But here they do not cancel, so the molecule has a dipole moment. That's another way of saying the molecule is polar. If a molecule consists of only 2 atoms, which you see here, the partial negative will be on the more electronegative atom, and the partial positive on the less electronegative atom, and those two values are always equal in magnitude. Like I said before, if the chlorine is negative 0.75, then the hydrogen must be positive 0.75. Alright, what about this molecule, carbon dioxide? So we have carbon in the center, double bonded to 2 oxygens. The double bond does not affect the polarity at all. So just think that there's a charge cloud on your left to an oxygen, and a charge cloud on your right to an oxygen. If we look at the electronegativity, oxygen is more electronegative than carbon. So both of those oxygens are pulling the electrons inside the bonds to themselves. And so we have an arrow going left and an arrow going right, and both of them have the positive charge in the center on the carbon. Those two arrows, left and right, they are equal in magnitude because they're both going toward the same atom, oxygen, and they're in opposite directions, so they cancel each other out. So this molecule is actually nonpolar, even though it has polar bonds inside it. The two polar bonds are symmetrical, and they cancel. So the dipole moment would be 0. Right? This molecule, water, is drawn bent, and that's very important because if you look back, the only reason these two cancel is because this molecule is linear. So if we draw a molecule linear that isn't actually linear, we may mistake it for being nonpolar. So let's look at water. In water, the shape is bent, so that's important to keep in mind. Remember, shape was one of our main factors. Inside water, the oxygen is more electronegative than the hydrogen. So the oxygen pulls the electrons toward itself that are inside that bond. This leaves both the hydrogens partially positive, and then you see the oxygen is partially negative. And there's a 2 in front of that because it's pulling from the 2 hydrogens, so it's got to cancel or equal to the positive on those hydrogens. This molecule is polar. The 2 polar bonds to the hydrogens are asymmetrically arranged, so they do not cancel. Those 2 arrows coming toward each other, they're not going to cancel each other out. So this molecule is polar. And we know that water's polar. It's a good thing water's polar. That's why we have salt water in the ocean, because salt only mixes with polar substances. Okay, so that's a good combination. Keep in mind water is polar, so if you draw it linear on accident and you think it might be nonpolar, bent molecules are polar. Alright, BF3 for another example, boron trifluoride. Now we know that fluorine is the most electronegative element in the periodic table, so it's going to pull the electrons toward itself. So each of those fluorines is pulling the electrons away from the boron. Notice the shape here, trigonal planar, and we know we have those 120-degree bond angles. This turns out to be nonpolar because these 3 are symmetrically arranged around boron. So the dipoles cancel and the dipole moment would be 0. Now, it was easy to see in carbon dioxide because you had like left and right, and that's really clear that that cancels, and here it might not be so obvious. But if you think about this as being, let me pencil out, this one here is like a little to the left, right? And a little down, if you had to separate it into 2 directions. And then this one is a little, this other fluorine is a little to the right, and also a little down. If you had to separate it into 2 directions, it's going right and down. So this left and right cancels, and the up and down cancels. Okay, if you're studying physics, it's the vectors that cancel. If you are not studying physics, you don't care about physics, just trust me that if they are symmetrical, okay, so trigonal planar is a very symmetrical shape. Tetrahedral is a symmetrical shape. If these are symmetrical, then they're going to cancel. But if they're non-symmetrical, like a bent shape, that's not symmetrical. Seesaw, that's not symmetrical. You can kind of look at your shapes and see the ones that have lone pairs in them usually end up being asymmetrical unless it's something like square planar or linear. So symmetrical, nonpolar, and then asymmetrical, those are going to be polar because the dipoles won't cancel. Carbon tetrachloride. We know that chlorine is more electronegative than carbon, so those arrows are all going to be pointed out. Remember, this is a 3D structure, okay? So all the arrows are going away from carbon, but they're going away from carbon symmetrically. So tetrahedral is a very symmetrical shape. So these 4 polar bonds that are symmetrically arranged cancel, and the dipole moment is 0. So that's a nonpolar molecule. Now, what if we take the same shape, still tetrahedral, but we're going to replace 3 of those chlorines with hydrogens. So now let's draw our arrows. Remember, I don't know if you, which video this was, but we talked about carbon and hydrogen. And that bond between carbon and hydrogen is not really polar. Okay? They share almost equally. But if we had to choose, carbon is a little more electronegative. So those arrows are going in toward carbon. Then you still have that one arrow going out toward chlorine. So you have 3 arrows in, 1 arrow out. Those are not going to cancel. So this molecule is going to be polar. That 1 arrow going out has no arrow to cancel with it, and then you have all your arrows coming in. So this molecule is polar, and it would have a dipole moment. The reason we're using that language is because that's the language of the AP exam. Is there a dipole moment is what they're going to ask. All right, what about ammonia, the popular cleaning product, NH3? This molecule has a trigonal pyramidal shape, which they tried to demonstrate there. So we have 4 charge clouds, like in tetrahedral, but one of them is a lone pair. Between nitrogen and hydrogen, we know that nitrogen is closer to fluorine, so those arrows are going to come in toward nitrogen. That's going to leave your hydrogen electron poor. So the hydrogen there you see has the positive, and then the nitrogen has 3 times the negative because it's pulling from all 3 of these. And then it also has its lone pair, which they're not accounting for, but that's going to add even more electronegativity there. All right, so you have your 3 arrows coming in. Let me draw this one more time. And they are not symmetrically arranged. If there was a 4th hydrogen up here and that arrow could come down symmetrically, then those could all cancel. But you have your 3 coming in, and then your lone pair throws off your symmetry. So you have 3 bonds asymmetrically arranged. The dipoles do not cancel, so it is polar. These points are kind of key when you start to write your own explanation. So why is something polar? If something is polar, it is because the polar bonds are asymmetrically arranged and the dipoles do not cancel. So you can steal this language. If something is nonpolar, it is because the bonds are symmetrically arranged and the dipoles do cancel. Okay, those are your 2 explanations. So if you want to go back and kind of highlight those, when you are asked to explain, this is the type of language that we want to use. All right, one last point to finish off this section is about something called diatomic molecules. Now, when we say diatomic molecule, we're talking about a molecule that is made of 2 types of atoms. Okay? What I mean by that is NH3 is a diatomic molecule. It's made of nitrogen and hydrogen. There may be more than one of them, okay, but it's 2 types of atoms. This CH3Cl, that's not a diatomic molecule. Okay, that's got 3 types of atoms in it. Carbon tetrachloride, that's a diatomic molecule where there's carbon and chlorine. So those types of molecules have 2 types of atoms. What they're thinking is, what if we took one of those atoms and replaced it with an atom from the same group? Okay. Instead of carbon tetrachloride, what if you had, what element is located right below carbon on the periodic table? Let's say you replace that carbon with silicon. So you had silicon trichloride. If you take an atom and replace it with an atom from the exact same group, it will have the same shape still, and it will still be polar or nonpolar, whatever it was before. So this gives us a lot of predictive power, and also it can save us a lot of time. So if we see CCl4 and then SiCl4, carbon and silicon are from the same group. So we know they're going to act the exact same. So if we know the properties of one, we know the properties of the other. Same thing if it's CCl4 and we change it to CF4. Well, chlorine and fluorine are in the same group, so we can replace chlorine with fluorine as long as we do it in the same proportion. And we can say, oh, those are going to have the same shape. This can help chemists design new materials. So they can say, I can take this element from one group and replace it with an element from another group, and this could lead me to a new substance with very similar properties. For example, silicon dioxide can be used to make ceramics. So maybe tin, because tin is in the same group as silicon, maybe tin dioxide could work just as well, or it may work even better. So this is kind of how we can start to design new materials, is not just, out of the wild, take some stuff and jam it together, but look at the properties of the things that we already have and then say, okay, how can we build upon this? Maybe because tin is larger, it might be a little more sturdy in that molecule, or maybe not. We'll have to explore to see, but at least we have some foundation from the silicon dioxide to kind of build upon. So that gives you an idea of how chemists can start to design new materials.